Hello and welcome back to Computer Science 3 CSCE 310. It's our last Friday. Remember, next week is only the first 4 days, Monday through Thursday. Thursday being the final exam that will use the lecture time as a review. And then, of course, just like the midterm, you'll have all day to complete that. You were given an extension for homework 3, which ran out last night, midnight. We will hope to have that graded early next week. And of course, you still have assignment 4 to do, which is also due on midnight of Thursday next week, same as your as your final exam. So keep those two final things in mind. Those are the last two things you would have to do for this course. In addition to that, also keep in mind that you have about 50 bonus points available on that last assignment. It's worth 250 points, but it's graded out of 200. So any bonus that you accumulate from that will be, of course, bleed into the remainder of your grade. So if you choose to do all of the programming exercises on that last assignment, then of course you could earn, help the rest of your grade. All right. So today we're going to be starting on our last topic, which is computation, computability, and we're going to be discussing a more theoretical side of computer science. So what we're going to be doing is the mathematical end of computer science. Okay, and it really puts a lot of what you've done over the first year and a half in a computer science program into perspective when you can start to look at the theory behind a lot of this stuff. So I'm going to go ahead and start out with giving you a motivational statement here, and then we're going to break that down. So first of all, consider the following statement. Algorithms solve problems. Now, before I talk about this actual statement, first of all, you'll note that I didn't say computers solve problems. I would never say that, as I've tried to hammer home in Computer Science 1 and 2 over and over again for years. Computers don't solve problems. Computers are dumb. The computers do exactly what you tell them to do, or exactly what they're told to do. They're just machines, automatons. That's a word that we'll come up with later on here. So humans solve problems, all right? Computers only automate solutions. So when I say that algorithms solve problems, I'm kind of making the same mistake there. Algorithms don't solve problems. People solve problems. People come up with algorithms. But forgive me for that a little bit. This is basically the crux of what's eventually going to be termed the Church-Turing thesis. What does this mean, though, right? Algorithms solve problems. I mean, that's not a very controversial statement. If anybody has read an algorithm or written an algorithm to solve a problem, they know, well, yeah, that's pretty straightforward. But to even talk about that, we need a much more rigorous formal basis. What are algorithms? What does it mean to solve something? And what are problems, right? We have kind of a good idea of what an algorithm is. An algorithm is simply just, a list of instructions for describing some process, right? Pseudocode, basically. But what does it mean that it solves a problem? It takes input and it produces output, right? So those are all fine intuitive definitions, fine intuitive understandings of each one of these three words, but it's still not enough. This is not a mathematically rigorous statement at all. This statement is intuitive, but plain old English. Right? It is not mathematically rigorous at all. So if I want to actually start studying the structure of algorithms, and we have done that a little bit up to this point. Given an algorithm, you can go ahead and analyze it and say, well, it's big O of n squared, or it's an exponential time algorithm, or whatever, or it goes beyond this course. But given an algorithm, you can prove that it's correct, that it actually solves the problem through an inductive proof or through some loop invariant of some sort, right? But the statement itself, the larger, more abstract statement that algorithms can solve all of our problems. Well, can they? Can I write a computer program to solve any computer problem, right? To start answering those questions, we need a much more rigorous and foundation than just a bunch of dictionary words, right? These all have plain dictionary definitions, right? The statement above is a dictionary definition of each word, right? That algorithms are a process for solving, for describing, or a list of instructions for describing a process, solving, or we could look that up, whatever Webster's would tell us about that. And a problem is a situation, we could go to websters.com, right, and look all these things up. I can't, it's very difficult to define something off the top of your head. You have to think about it. And so, but you could run to a dictionary and you could define each one of these things. We need a better, that is, more rigorous mathematical statement. And that statement is going to be as follows: that Turing machines decide languages. Right? And I'll go ahead and capitalize each one of those things. Right? So you can see that there's a one-to-one correspondence here with the words in these two statements. Algorithms solve problems. Turing machines decide languages. Well, what do we mean by algorithms? We mean Turing machines. What are Turing machines? We'll get to that. What do we mean that? What is the connection between solving a problem and deciding something? Right? What is the connection between a problem and a language? The difference here is that each one of these three things has a rigorous and precise mathematical meaning and definition that we're going to go over now. But that now we are in the realm of mathematics. Now we can prove things because we actually have a definition that we can work with, rather than just a Weasley, Webster's, whatever Webster's says kind of definition. Okay. So I'm going to go ahead and start at the first part of this, where I'm going to define what a language is. Right? It's not a language in the sense of natural languages. Right? So languages. We of course have natural languages: English, Japanese, Korean, Spanish, etc. Those are all natural languages. Natural languages do have structure, and attempts have been made to shoehorn natural languages into a mathematical model for speech recognition, right? Natural language processing is big right now, or it's big again now, NLP, and for various reasons. But what we mean by languages in the sense of computation is simply just sets, right? And everybody knows what a set, everybody here at least in computer science knows what a set is. So kind of like what we did with Huffman coding. Let sigma be a set of 0, 1. Right? Now this is our alphabet. And it's going to, now you can go ahead and expand your alphabet to be 0, 1, A, B, C, D, E, F, G, whatever, right? You can go ahead and expand your alphabet out if you want to, but as we all know as computer scientists, you don't need to do that. You only need to consider binary, right? If you've got an alphabet that has A, B, C in it, right, then the ASCII text table says you can go ahead and encode those as binary strings, just like you did on the second assignment with Huffman coding. You took a plain text file and encoded it in binary, and so it's enough to consider 0 and 1 as your alphabet. A string or word over sigma is a finite sequence of symbols from sigma. Right. So, for example, right, if I've got if I've got a binary alphabet here, then of course the string 0, right? That is a a string because it's just a string of length 1. Also, 1 by itself is a string, right? And then we can have any sequence of zeros and ones. Right? Me just mashing my keyboard there, all right, etc. Each one of these is a finite sequence. It's ordered, right? And you can also have, you know, we're not treating these necessarily as numbers. So you can have a bunch of leading zeros, 1. That's not the same thing as the second one there with just the 1, right? These are two distinct strings. This one right here is of length 1, and this one is 1, 2, 3, 4, 5, 6, 7 characters, right? Or 7 symbols from over the alphabet. There's also a very special character that we need to make this a fuller algebraic structure, and we use sigma. No, it's not sigma. Dang it, lambda. That looks right. There we go. Is the empty string, right? And this is necessary for if you're going to concatenate things together, you need an identity element. So if I concatenate 0 and 1 together, I get 0, 1. But if I can concatenate lambda, the empty string, with another string 0, 1, 0, then I get 0, 1, 0 back. You need an identity element under certain operations to give you a more algebraic more structure to what you're talking about. We're not going to get into it that deeply, though. But know that there is the empty string. And you can do this in programming too, right? You have strings all the time in programming. And you can have the empty string, the string of length 0, right? Where you just put 2 double quotes and there's nothing in between. That's not the same thing as like the null terminating character in C. That's not the same thing as 0, etc. It's not the same thing as the string containing 0, right? These are all distinct things. The empty string is something completely different, okay? All right. Well, then sometimes people use epsilon. By the way, I'm using lambda to describe it, right? Or to denote it. So the set of all finite strings over sigma is denoted as sigma star. And you might recognize this already immediately. Where do we use the star operator in computer science? We use it all over the place. It's on the command line. It's a wildcard, right? Remove star, right? You're removing everything, all files. It matches everything, or everything .exe, that will match all executable files, or .txt will match all text files, etc., right? That star there is actually used in regular expressions, matching. If I want all instances of A or AA or AAA, right? I would say A star, 0 or more characters, 0 or more instances of whatever sequence I'm defining. If you're not familiar with regular expressions, I highly recommend that you get familiar with them because they're so useful. But that goes beyond the scope of what we're looking at right now. So, a language. Now this is where we actually can define a language, now that we've got all that terminology there, is a subset, L, of sigma star. There we go. And there, yeah, now it renders there, right? So why is that equivalent to a problem, right? My claim here is that languages are equivalent to problems, right? That's what we started out with, right? I wanted to say that these 3 terms, algorithms solve problems, are equivalent to Turing machines decide languages. So we're starting out with problems and languages. Why is it enough to consider languages when you're trying to talk about problems, right? Just a second. Let me fix this. There we go. All right. Any questions? Remember, we are on Piazza for a live Q&A. So if you have any questions, please go ahead and chime in there. All right. So I'm just skipping over some other language stuff. Languages have a lot of operators that you can play around with. Concatenation. You can combine things. Since languages are sets, L1 and L2, you can take the union. You can take the intersection. You can do a lot of. You can take the complement. Any set operation that you can think of can be applied to a language, and then you're playing around with languages themselves. Right? And this kind of makes sense too, because if we had said that sigma was A, B, C, D, E, F, G, or A through Z instead, then we would kind of be saying that, well, our language is some subset of finite combinations of those things. So HELLO, that's a finite word formed from that alphabet, and that is a valid word. But FFGDPT, that's not a word, right? That's not a word in our language. So there are elements that are in the language, but not out. And there are other words that are not part of the language, right? You can add language with natural languages. You can invent new words all the time, right? And people do that slang, right? New words come into existence. Language is abused all the time to get that. So my claim here is, again, that languages are equivalent to problems. How does that work as far as computer problems go? So recall that an instance of a decision problem involves a configuration of data, right, input, as well as determining as well as a question, a yes or no question, I should say. Yes, no question, right? Again, another example would be given a graph G, is it acyclic or not, right? In other words, is it a tree? Given an integer x, or x, is it prime or not, right? Or composite, right? Given what else have we looked at before? That's a yes or no question. Given a graph G, does it contain a Hamiltonian cycle or not, right? These are all decision problems because they all have yes or no answers, right? So why is a language equivalent to a problem? You can define a language that encodes or models a problem, and then your decision question becomes, given an input x, is it in the language or not, right? In other words, x is a yes instance. Yes, it has a Hamiltonian path. Yes, it is acyclic. Or no, right? If x is in L, x is a no instance if x is not in L, right? There. So you just have to formulate the question correctly. Let's look at some examples, right? What I'm going to do is I'm going to define a language where I have all G such that G is an acyclic graph. All right, that's not rendering correct. Text RM. There we go. All right, that'll work. So what I want is a set of all graphs that are acyclic, right? That doesn't quite jive with our definition so far, where a language has to be a bunch of binary, but we can make it so, right? As above, an integer x such that x is prime, right? A graph G such that it's Hamiltonian or not, right? To reconcile a problem with our definition, that is, take a problem and turn it into a language, we need an encoding, right? And again, you've done this before with Huffman coding, right? Given, say, a graph G, you can produce an encoding over, and we denote that with Langle-Rangle. So Langle G Wrangle. There we go. It ends up looking like that in LaTeX. It's just it's not a less than greater than sign. It's these special things that are used in some other instances in mathematics to denote things. But we're going to use it in computability theory here to say that that's an encoding of a graph, of the graph G. Right? And you can do this all the time. Right? Let's go over to an example that we were looking at yesterday or maybe the day before. This weighted graph. Right? There's the weighted graph. Right? I've just encoded it over a different alphabet. I've encoded it over the alphabet of numbers that includes numbers 0 through 9, a period, an end-line character, and a space. Right? There's nothing stopping me from simply encoding that as binary. In fact, I'll show you how to do it. It is already encoded in binary. Why? It's already on a computer. Right? Everything on a computer is already in binary. So all I did was take that file and dump it to a binary representation here. Now ignore the first column here. That's the byte offset. Ignore the right column. That's actually the actual ASCII text characters being rendered. But 1, 2, 3, 4, 5, 6. The inner 6 columns here. That's my encoding. Right? That's my encoding of this graph. Of course, you could look at it from another angle that you would assign binary numbers to each one of the vertices, and then you would have a delimited list of edges, just like we did in the text file. And you'd have to keep track of some delimiter. In this case, in the text file, we're keeping track of the delimiter as being a space and end-line characters. All we have to do is encode those as other binary strings. And we could even be more efficient about it and use Huffman coding to encode it into a prefix-free encoding, so that I don't have to use bytes all the time like this. But the thing to realize is that you do this all the time, right? Any problem can be encoded in binary, right? And so we're already in the realm of languages, right? Thus, any problems are the same thing as languages. And all you have to do is ask the question, I'm going to define a language. I'm going to define a language such that, like I did up here, such that G is an acyclic graph. So all I have to do is do it as an encoding instead. Right? So Langle, Wrangle, right? Langle, there we go. All binary strings which represent an encoding of a graph G such that G is an acyclic graph. Right? Now there is a technical note here. All invalid encodings are ignored. Right? They're not in the language. Right? So you could say that you could say technically that they're in the complement language. It's just a little technical detail. You can define the complement language to say that all G such that G is contains a cycle. And that would be the opposite, but then you have this disconnect. You have all these invalid encodings, right? Where I don't provide a space delimited list of vertices along with their weights. That I just randomly type blah blah blah, mash my keyboard, right? And those would not be that's just a technical detail. Those would not be in either language, but we can move on without too much problems on that front. So languages are problems, and all you need to language. There we go. Not in the language. All right. So hopefully I've convinced you of that. If not, again, all you have to do is look at a computer. Everything that every problem that you've ever solved is on a computer is, well, at the end of the day, it's a bunch of binary running across a bunch of wires, right? So anything can be encoded as a binary string. Right? What we need to do now is reconcile the other parts. What is it? First of all, what is a Turing machine, and what does it mean to decide a language? Well, given a language, right? given a language and an input string x, we need solving the language simply means determining whether or not x is in L. And I need to get that. Given a language L and an input string x, solving the language simply means determining whether or not it's in L. Ooh, sorry, I need to take care of something. I'll be right back. All right, sorry about that. So before we go on to talk about computational models and Turing machines, I do want to take care of one other technical detail, right? So these definitions, terminology, only take care of only take care of decision problems, right? Problems that have a yes or no answer. Now you might be thinking to yourself, there are lots of other types of problems out there. If we only restricted ourselves to decision versions of problems, then that would be like in programming only having functions that return Boolean values, true or false, right? And that would not be very convenient. I mean, you can do it, but it would not be a very convenient way of being able to program stuff. It turns out that it's only a technical detail, right? You also have optimization problems, right? For example, what is the value of the minimum spanning tree of G, right? Right. That's a number, right? Where you're actually trying to optimize and minimize a number. The output ends up being, if you want to look at it from just the optimization point of view, the output ends up being not yes or no, but an actual number. The minimum spanning tree's weight is 39, right? Or you also have functional problems, right? Not only do you want to know what the value of the minimum spanning tree is, but you also want to output it, right? Or for Hamiltonian path, for example, you not only want to know if there is a Hamiltonian path or not, but if so, what is it? Here, the output is a path, right? It's a sequence of vertices. Up here, the output was a number, right? It turns out that it doesn't really matter if you want, because you can take an optimization problem or a functional problem, and you can simply just transform it into a decision problem. Here's how. I'll show you for the first one here, optimization problems. Consider the following language, right? And I want to cut and paste this up here so I don't have to type a lot. So I'm going to encode a graph, and I'm going to encode a value w, right? So the condition on this language will be that G is a graph whose minimum spanning tree, MST, has a weight of w. There we go. All right. So do you see the trick there? All right. All I did was take the optimization, the output, and I simply just added it as part of the encoding of the input, right? And now, now it becomes a decision problem, because if I've given a graph and I say, I can ask the question: is this graph, is its minimum spanning tree value, is it 39? The answer is yes or no, right? That means that it could have a minimum spanning tree that is larger or smaller, right? But I don't know. I don't know that, because this is just a decision problem. But it doesn't stop me from asking that question over and over again, right? Kind of like the Price is Right game, where they have to guess the price. The smart ones do binary search. They see a product that's not worth no more than $10. So I'll guess, is it worth $5? No, lower. Okay, is it worth $2? No, it's higher. Right, and then they ask the question over and over again until they zero on the value. So you can do the same thing with a minimum spanning tree by simply just taking all the weights, summing them all up. And if they're like over here, all the weights are 5, 3, 4, and 2. So that'll be, what, 14? All I have to do is ask the question, is the minimum spanning tree, here's the graph, is the minimum spanning tree's weight 5? Right? No. No. Okay. Is it 6? Is it 7? You can be inefficient about it. Is it 6? Is it 7? Is it 8? Etc. You can also change your condition here. Has a weight of at most. Right? And then you can exploit binary search to do this for you instead. Right? So it's just a small technical detail. With respect to the functional problem, you can actually encode the path as a part of the graph. That here's a graph, here's a path, and it's in the language if this is a valid Hamiltonian path in the graph G. Or you can look at it another way, the complexity theorists do, where you're outputting just a bit at a time. So the ith bit of the output is 0 or 1 of this input over here. It's just a small technical detail that you have to get over. You can encode any problem, regardless of what type of problem it is, as a language. Okay? All right. So let's talk about computational models. We're not going to. We're going to eventually talk about Turing machines today, but before we do that, let's look at a simpler model. Right? To start, let's consider a simple, what is called a finite state automaton. There we go. Automaton is kind of an archaic word. It's in fact predates computers. Right? Any mechanical device would be considered an automaton. There was a parlor trick where there was this I forget what it was called, but there was an automaton that supposedly played chess. Right, there was this robotic man that they built in several hundred years ago, and it was being controlled by somebody underneath. It was not real automaton. It was not automatic. It didn't run by itself. Somebody else controlled it. So an automaton in the traditional sense is just a machine that runs by itself. Right. And in this case, a finite state automaton is just a very, very simple model of computation. So an finite state automaton is a 5-tuple. Here's the mathematical definition, the rigorous mathematical definition coming in. Q, sigma, delta, Q naught, and F. All right, oops. There. And each one of these has an explanation, right? So Q is a set of finite states. Right? Sigma is our alphabet. And for us, it's just going to be 0 and 1. Of course, you can expand that if you really want to. The most complex part of this is going to be delta, which is a function. It maps the finite states and an input value, should be sigma, right, to the set of finite states. And I'll come back to that and explain that a little bit more. And then, of course, Q naught, we have to start our computation somewhere. Right? So Q naught is kind of like our main. Right? And this is on initial state. And that's where you start. Okay? And then F, which is a subset of states, is a set of accepting states. Okay? So to understand this, first let me draw you a picture of a simple finite state automaton. Okay, and so this is going to have three states: Q naught, Q1. I forget what this computes, but we'll go ahead and figure it out together. And Q2. I'm going to put a double circle around here to indicate that this is an accepting state. And by exclusion, these two are going to be rejecting states. All right? So Q naught is our initial state. How do these states relate to each other? The idea here is that we have that transition function, that delta. If I come in here and I'm looking at the input, if the first bit of the input is 1, say I'll stay in that state. This is just one example, of course. You can come up with infinitely many different finite state machines. If we see a 0, however, we'll transition to a new state over here, to this Q1. Now, since we've restricted our alphabet to 0, 1 binary, those are the only two possibilities, or at least for a deterministic finite state machine. Don't worry, there are non-deterministic finite state machines where you can essentially magically jump from one state to another state. We'll discuss that when we get into P and NP, the N standing for non-determinism. All right. When I'm in Q1, if I see, say, a 0, then I will stay in the state. Otherwise, if I see a 1, I'll go ahead and transition over to Q2 here. Okay. And if I see in Q2, if I see a 0, I'll go back over here. And if I see a 1, I'll jump back to the first state over here. Right? There's my finite state automaton. Right? Depending on the input, I would simulate the computation on a particular input by transitioning to each one of these states. If at the end of the input I'm in one of these rejecting states, then I say that the input string is not in the language. If I'm at the end of the input I'm in an accept state, then I say that the input string is in the language. So let's look at some examples. Let's see. Do I have a list of... nope, I'll just make up strings. All right. So first of all, what about 0, 1, 1, 0? Right. There's my input. Let's simulate the computation on that input. We start out by looking at the first bit. So we start out in this initial state here. We see a 0, so we transition over to this state. On the second bit, we see a 1, so we transition over to this state. The third bit, we see a 1, so we end up transitioning back over here to the initial state again. And you can see that there are cycles in here. That cycles are perfectly fine. Because we're only reading the bit once. We're never going back and forth. In fact, we're only reading it one way. We start here and we work our way right. We can never backtrack and look at a bit again in this model. The last one is 0, and so we end up rejecting it. All right? So we say that 0, 1, 1, 0 is not in the language defined by this automaton, if I call this automaton A. Okay? What about 1, 1, 0, 1, or 0, 1? All right, let's look at that. So 1, I transition and I stay in the state. Another 1, I transition, stay in that state. 0, and then 0, I stay in that state. 1, I go over to the accepting state. So we accept. Right? And 1, 1, 0, 0, 1 is in the language A because we accepted it. Right? Some other corner cases here. What about the empty string? Right? Lambda. Well, all we're doing there is we're not reading any of the input. We start out in the this initial state here, and we end up rejecting it. Because it's a reject state, we end up not going anywhere. Right? You see this kind of model of computation all the time. If you've ever written a loop with a switch statement in it, right, you're basically doing a finite state machine that goes over and over and over and over again. What are some conditions? Do I change the state? Let's see. What's an example? Usually is in game programming where a character is alive, and then it saw an enemy, an NPC game character. It sees the main player, so now it's in an attack state, and so it has different behavior. But prior to that, it was just in a scan state. It was looking for an enemy to destroy. Then it went into an attack state, and then a GTA style, you ran off and the NPC was stupid and it lost track of you. And so, okay, well, I'm going to go back to my roam state, right, until I see them again. And then the state is dead because you've killed off the character or something like that, right? So we end up rejecting it and we say that it's not in the language. Any finite state, any finite string, you can simulate the behavior on this finite state machine, and then you can come up with an answer that it's not in the language or it is in the language. Therefore, we say that this finite state automaton decides whatever language this happens to be. Right? Does anybody know what language this is? Right? How could we write this in plain old English to get a description of it? We only end up in this final state if we've seen 0, 1, or 0, 0, 0, 0, then a 1. So if we ever see, after that, if we ever see a 0 or a 1, we jump out of this. In fact, if we see a 1, we jump all the way back here and have to see a 0, 1 again in order to get back to that accept state. We can see as many zeros as you want, but we actually have to see a 0, 1 in order to get to that accept state. If we see a 0, well, we only have to see one more 1 to get back to that accept state. So what is the language in this case? It's the set of all strings such that x ends with 0, 1. Right? Cool. Right. So that's kind of a toy example. But you can imagine how you could use the simple power of this finite state machine to do some I don't want to say like hugely powerful, but certainly more powerful stuff than just, that it ends with a 0, 1. For example, what if it were to end with just a 0 or a 1? Can you distinguish those? Yes. Let's look at another example here. Basically what I want is, here's another language. I want all x such that x represents an even integer in binary. All right. So we can pretty much do this with just 2 states, I believe. Here is a rejecting state. Here is an accepting state. And it's even if and only if it ends with a 0. So if it ends with a 0, then that's fine. If we have 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, as many zeros as you want, then you stay in this accepting state. But if you ever see a 1 at the end, then you jump back over here. But then you saw another 0, so you jump back over there, right? And so you can go ahead and make a very simple finite state machine. This is our initial state because the empty string is not is neither, so we're going to throw it out of that language. And here's a very simple 2-state machine to determine whether or not something is even or odd, right? Because if it's even, then it's in the language, right? 1, 0, 1, 1, 0, right? This is in the language, and I'll call this E for even. And 1, 0, 1, 1, 1, it ends with a 1, so it's not even. It's not in the language. We could say that it is in the complement language, LO, where O is odd, right? And all I'd have to do there is flip these 2 states, right? Make this one a reject state, make this one into an accept state. So that's simple. We can do something even more powerful. So let me go ahead and define a parity. If the number of 1s in a binary string is even, it has even parity. Right? Parity, equality, kind of, that they're on parity, they're on the same thing, so they're all balanced in some sense. Even parity or zero parity. It's even, so it's zero. Otherwise, if it's else, if the number of ones in the string is odd, it has odd, that is 1 parity. And you hear this all the time with networking stuff and other stuff, where it's one of the simplest ways of doing error correction, error detection. Just count up the number of bits in a string that you're trying to send over a network, and it has 0 parity or odd parity. I'll go ahead and send that parity bit on as well, so that you can check at the other end that the parity bit doesn't match what I actually received, so there must have been an error in transmission. And you can detect, and not necessarily correct, but you can actually detect all odd bit flips, right? So if an odd number of bit flips got flipped, odd number of bits got flipped, then you can detect that with just one more bit, right? So it's a super convenient and efficient way of detecting certain types of transmission or storage errors. What does that look like with respect to a language? Well, we'll go ahead and define this language to be all x such that x has even parity. All right. Again, another two-state finite state automaton. All I need to do is create 2 states here. Right? And the first state here, if I see a 1, I'll transition over here because I will reject it. I've only seen 1, 1. But if I ever see another 1 that matches it, I'll go ahead and go back to this and put this into an accept state. Okay? Now the zeros don't matter. So if you see a 0 and you've already seen an even number of 1s, and you see a 0, well, that's not going to affect the parity at all. If you've seen an odd number of 1s, that's not going to affect the parity at all. So if you see a 0, and so stay in that state. Right? Make this the initial state, and you end up accepting the empty string because, well, yeah, it's even. 0 is an even number, right? It has 0 1s, therefore the empty string has even parity. Right? And there's a nice little finite state automaton that can do actually something pretty powerful and pretty useful. Right? You also have finite state machines in, a vending machine is the usual classic example where people put in quarters and so it changes its state to, 25 cents has been put in. Somebody puts in a dime and it transitions to a state that says 35 cents has been put in. And only when it reaches $1 or whatever they're charging nowadays in vending machines, way too much, then it says, okay, now you can go ahead and select what you're doing, right? What soda you want or whatever, right? So lots of useful stuff can be built out of finite state machines. Super simple to implement, to create, and of course super efficient to just put on a chip directly, a dedicated chip if you really wanted to. And it's not done anymore, but you can breadboard it really easy, right? So that's what a finite state machine is. A finite state machine, finite state automaton, defines a language as follows. On input string x, it reads it bit by bit and transitions to a new state according to that delta function. Right? If at the end of the input string the machine is in an accept state, we accept the string and say that x, which is in the language defined by the finite state automaton. If at the end of the input string the machine is in a reject state. We reject the string, reject the input, and say that X is not in the language L. Right? Some other caveats here. The input is read only and one-way read only. You cannot reverse the reading. Right? You can only go forward. There is no extra storage, no memory, or data structure. Right? It's an extremely simple but still powerful model of computation. Right? It can compute a lot of stuff, but there are some things that it can't compute. It can compute the parity, but it can't compute, say, whether or not X. It can compute whether or not X is even, but it would not be able to probably. I'd have to think about this. It's way. Yeah, I'm pretty sure, but it would not be able to compute that X is prime or not. Right? It would certainly not be able to compute whether or not a given graph is Hamiltonian or not. Right? I can say that definitively. Well, maybe no. Maybe that's still an open question, but probably not. Right? So what about that delta function? What does that look like again? Again, it's delta takes Q cross product with the sigma and transitions to a new state. Let's look at what delta looks like for this. Right? Again, delta is a function that maps a state, a current state, paired with a single bit from your alphabet and transitions to a new state over here. I did this pictorially. I just drew this picture. And it was enough to understand. But if you were to actually do this mathematically, then all you have to do is, they're called Caylee tables. All you have to do is write out the transition, we'll just call them transition tables here, where here's the delta table. Here's the transition table. Here's Q, sigma, and the new Q. Right? I need to give these names. So I'll call this A and this one B. Right? So if I'm in A and I see a 0, or if I'm in A and I see a 1, then this is the new state. If I'm in A and I see a 0, then I stay in A. If I'm in A and I see a 1, then I transition over to B. There are only two other possibilities here for such a simple finite state automaton. If I'm in B and I see a 0 or a 1, then if I'm in 0, if I see a 0, I stay in B. Otherwise, if I see a 1, I go over to A. Right? And it's that simple. Right? Q naught here is going to be A. And the set of accepting states here is going to be simply just A, which is a subset of Q, which is A, B. Right? So all of these things have rigorous mathematical definitions, a nice little Caylee table defined by a function, sets, subsets, states. Right? So now we have an actual mathematical definition of our first computational model. Right? It's extremely simple, but it's still powerful. You can compute a lot of stuff with finite state machines. Right? And it's quite common to program finite state machines using switch statements and other stuff like that. Right? All right. So that gives us our first clue as to what we mean by decides a language, right? So a computational model, or a finite state machine, automaton, or what we're going to look at eventually, a Turing machine, decides a language if it always always terminates on any input, and 2, okay, that's rendering good. For all inputs X in the language, it accepts, and for all inputs X not in the language, it rejects. Right? So the second piece of the puzzle is in place. Algorithms solve problems simply means that we come up with some computational model that decides a language, that always terminates. That's always going to be the case with a finite state automaton because of how it operates, so the way that we defined it. It only reads the input once. It never goes back and forth, and therefore there's no possibility of it getting stuck in an infinite loop. Right? It's powerful, but still simple, and too simple for our needs. What we need to do is we need to introduce another more powerful model of computation, and those are going to be Turing machines. Named for, of course, Alan Turing, who came up with the idea, and also the Church-Turing thesis, which is basically what we're talking about right now. Church comes into it because of lambda calculus, but and so we have to give due credit to everybody. But Turing came up with this idea, and came up with the idea that, in fact, these things that are now called Turing, I don't think he called them Turing machines. Nobody names stuff after themselves unless they're very, very egomaniacal or whatever. Whatever he was calling them, he said these are the things that we think of when we think of computation. This is a good definition, and that's why it's called a thesis. It's not a theorem. It's not something that's provable. It's whether or not you accept it. Yeah, that seems reasonable. That's what we mean when we think about computation because of this disconnect. This algorithm solved problems, that is a dictionary definition. So he came up with the idea of these Turing machines that decide these languages, and that's a rigorous mathematical definition that seems to align with this notion up here. That's the Church-Turing thesis. It's not a theorem because you can't say that this thing is equivalent to this thing, because this thing is in the realm of natural language, this thing is in the realm of mathematics. If you had two computational models, say Turing machines and finite state machines, then you can ask the question, are these two models equivalent? And you can come up with a theorem and proving that, yes, they are equivalent, or you can come up with a counterexample, another theorem that says, no, they're not equivalent. This one is more powerful than this other one. And you can do that in the case of finite state automatons versus Turing machines. But there are theories of models of computation that are equivalent. That's where Church comes in. He came up with something called lambda calculus. And the lambda calculus, is that the same thing as Turing machines? That is, any problem, any language that is decided by the Turing machines, can it also be decided, whatever that means for this calculus? Is there an equivalent calculus over here that you can do that you can solve that problem? And it turns out, yeah, you can, and any problem over here can be decided by a Turing machine, has an equivalent Turing machine over here. You need all that mathematical foundation, that mathematical definitions, in order to even ask that question properly. All right. So what are Turing machines? Turing machine is a 7-tuple. A Turing machine, TM for short, is a 7-tuple. Which is Q, sigma, should be delta? How does that render? Nope. I don't know my Greek letters. Okay. Google, help me out. Or Wolfram Alpha, what is that? Gamma. There we go. Now I can go ahead and... There we go. And another transition function, delta. Q naught. Q accept. ACC for short. And Q reg or rj reject for short. Okay. So some of these things are the same. Q is a finite set of states. So it's still a finite state machine, but it has much more powerful, and we'll see why here in a second. Sigma is the input alphabet. Gamma is the output alphabet. They may be the same. In fact, it'll be helpful for us to say that they're the same. They're just binary. The input, it can be binary. Well, then the output can be binary, right? There's no problem with us just boiling everything down to a bunch of ASCII text values in binary. The transition function, however, is a lot more complicated. So bear with me here. It's going to be, in fact, I'm going to go to the next line. Transition function is delta takes a state. It also looks at a bit of the input, a single bit of the input. It also may be looking at, or it could be ignoring, a single bit of the output. And then it transitions to a new state. It writes something on the output, we're going to call it a tape here in a second, gamma. And it transitions both on the input and the output times left, right, or stay the same. Two of those things, and don't worry about it. We'll talk about. I'll give you another visualization here in a second. Q naught is on initial state. Q accept is on accepting state. If you unlike a finite state automaton where you can have multiple accepting states, you can have multiple accepting states in a Turing machine, or you can just go ahead and change it so that you that you only have one, right? You consolidate them all down to one, because what happens in an accepting state and a rejecting state in a Turing machine means that the machine stops, right? And Q reject is a rejecting state. Okay, there we go. So I'm going to go ahead and simply just steal my own picture over here so that you can get an idea of what this looks like. Right? There is a pictorial depiction of a Turing machine. We have what's called an input tape, and we have what's called a work tape or output tape, whichever one you want to look at, think about it. In the input tape, we have input, x naught here up to xn. I wouldn't do it that way. And then after this is a special symbol that indicates that that's the end of the input. You only have, in this case, n plus 1 bits. Okay. And then after that, the input tape has to be finite because you can't have infinite input. There are computational models that consider infinite input and infinite outputs. We're not going to consider that. This is a simple Turing machine, right? So this special symbol right here is an oops, that's not what I wanted. But I do have color. Okay, this special symbol right here indicates an empty or an uninitialized cell in the output or in the input. The work tape is similar. We also have those symbols over here to indicate that nothing has been written to that cell yet. But otherwise, what we have are these two pointers, if you want to think of them that way. But they're sometimes called tape heads that are pointing to a particular input string and a particular output string or work tape string. And inside this finite state control is a whole bunch of states, Q, right? And whatever state we're in, we look at the input, right? This one. We look at the output, this one. And then we make a decision. And we inside this finite state control, we transition to a new state. And we possibly write something to the output. And then we move the input tape head left or right, or it stays the same. That's what this stuff right here is. Likewise, because we're doing two of those things, we can also do the output tape. It can move left, or it can move right, or it can stay the same. Right there. Cool. That is a Turing machine, and guess what? Every single computer that you can ever hope to build, is no more powerful than this model right here. That's the Church-Turing thesis. That's that's what this is what we mean when we think of an algorithm, right? It's a very simple computer. Of course, you could build this if you really wanted to out of actual circuitry. Nobody really ever wants to do that. Why? Because you end up with extremely complicated. It's an extremely complicated, convoluted way of doing things. For example, here's an extended example in the book. Oops, let's get rid of that. A 3-state Turing machine with possible inputs and possible outputs, just with only 3 states by itself, actually 5 states with the accept and reject states here. Then I had to write this entire table here to define the transition function, the delta function over here, right? It's like writing an algorithm in pseudocode at a very high level, abstract, versus writing a Turing machine at a very low level, right? In real life, it's like writing in Java versus writing in assembly or literally in machine code, right? Way back when the computers were new, you did have to write in machine code. You actually had to take the punch cards and punch out the tab for a 0, leave it for a 1. You actually had to program that way. Of course, you started out on a blackboard and you wrote down your algorithm, then you translated that into the machine instructions, and then you went over and you punched things out, right? And then you hoped that you didn't have a bug where, oops, I meant to punch that out. Didn't mean to punch that out, and I did. Gonna have to restore that with a little piece of cellophane tape, or you punched it out, but then there was a hanging chad there, and that it got put back in, and now your punch cards don't work. It's got a bug in it somewhere, right? Not something that you want to do, and this certainly not something I want to do. I built this machine just to show you how complex it can be, just to do something simple. What does this one do? Well, it looks like this, right? I won't even tell you what it does. Let's see if we can figure out what it does. I'll start in this state here, and if I see a 0, and it doesn't matter, these dots here are to indicate it doesn't matter what you see in the output tape, then jump over to this one and move the input. The input tape doesn't go anywhere. The output tape moves right after having written this hash value here to it. Okay, I wonder what that is. I'm staying in this state here. If I see a 0 and an empty on the output string, then I write a 0 to the output string and transition both the input and the output right. I move on. Otherwise, if I implicitly here, if I see a 1 and on the input tape and nothing on the output tape, then I write nothing on the output tape and I stay where I am. Right? So what is this doing? You can stare at it for a long time, or you can try to write out. Okay, it seems to accept this string. It seems to not accept this string. Here's the language that it defines. All it's doing is finding binary strings that have an equal number of zeros followed any number of zeros followed by an equal number of 1s, right? And that's it. Where n is a non-negative integer, it doesn't matter, right? Of course, you can't have negatively sized strings, so this is an integer, right? So in other words, it would accept 0, 0, 0, 1, 1, 1 because there are an equal number of 1s as there are zeros. It would reject these are okay, 0, 0, 1, 1 or 0, 1, right? And I'm not sure, does it accept the empty string? It does not look like it does. Oh, wait, that's just a small detail. But what if it started on 1, 0, 1, 1, right? Well, if we start out in a state over here and we see a 1, we jump immediately to this sunken reject state down here, right? And so we would end up rejecting it. All right, so this is no, we don't accept that one. Nothing that begins with a 1. It has to begin with a 0. And what we're doing with the output tape, with these hashes, what we're doing is every time we see a 1, we write a hash, we write a hash, we write a hash. The first time that we see a 1, we start deleting those hashes. And if that's the input and we still have a hash there, then we jump over to this reject state. But the computation over here, it's basically using the output string as a stack. by writing hash 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 for each 0 that it sees. So this one, it would have written hash hash hash. Then it goes into, oh, I see a 1, so I'm going to go ahead and get rid of that, get rid of that, get rid of that. And guess what? Now I accept it because there were an equal number of hashes that I wrote down with zeros that I then canceled out with ones. All right? If you ever see 0, 0, 0, 1, 1, 1, that's close to being accepted, but then if we see another 0, then we would end up with an invalid state, and we'd go to the reject state. That's how this is defined. It is not pretty. Writing out Turing machines is definitely not an exercise that I would ever give anybody, except maybe in a complexity theory course or something, but only as a busy work exercise to indicate, to really drive home the point that nobody programs Turing machines, right? Directly, as a matter of course. Of course, you can do it for fun. You can write a Turing machine simulator for fun, right? And that actually is fun, right? But then actually doing everything by writing Turing machine code, like this code that we had before, right? Not fun. I had to go through even for 5 states, I'm only focusing on 3 here, 2 possible inputs. That's going to be how many possibilities? 1, 2, 3, 4. 4 times 3, so 12, 36 different possibilities. And for each one of these, the NA, I had to put that in the transition function anyway and say that some states are not possible, right? Just because they're not reachable, or some configurations are not possible. But I had to go through and identify all of those, right? Not fun to write that out. Certainly not something I would expect a student to do, right? At least for this course. Right? But now that gives us an idea of Turing machines accepting a language. So a Turing machine decides a language L if and only if it halts on all inputs and accepts or rejects if X is in L / X is not in L. Same definition as before. The key here is the halting. Right? Let me draw a Turing machine that would have an equivalent program in a Computer Science 1 course. In fact, I don't need to draw too much. Q not. Doesn't matter. Right? Here's our accept and reject states are over here. I'll never get to them because there's no transition over there. 0, 1, it doesn't matter. I will always stay in this state. Right? Now, unlike a finite state machine where you would just read the input once and you'd be done and you'd stay here and you'd halt because you exhausted the input, a Turing machine doesn't do that. A Turing machine only halts if it jumps to this accept state or this reject state. So you have an infinite loop here. Right? And that's perfect. I mean, you can design Turing machines like this, just like you can write a computer program to have a while statement, while 1, right? Do nothing. That would certainly, this simple while loop here in a C program would certainly end up in an infinite loop. Right? We don't like infinite loops. Well, we don't like infinite loops where they're not supposed to be, but certainly we do like infinite loops in, say, poll loops. This computer that I've got on, it's in a constant poll loop. It is an operating system that is looking at each process and saying, okay, yeah, this process needs to do something, this process needs to do something. Then it goes back and it runs forever until I shut it off or something catastrophic happens and it dies. I want my computer to run forever in an infinite loop because I don't want it to shut off without me telling it to stop, right? So sometimes you do want infinite loops, and sometimes infinite loops are necessary to be fully to be computable, right? A Turing machine is equivalent to any programming language. That's the thing that I want you to take away today, and this is where we'll end it. That any program that you write, any computer language, C, Java, what you're doing right now, Python, right, has an equivalent Turing machine representation. And any Turing machine that you come up with, of course, you can go ahead and write a Java program to simulate that Turing machine. Right? That one is easy to see. Maybe this one is not necessarily as easy to see until we start looking at what's called the universal Turing machine. Right? So hopefully I've convinced you of the Church-Turing thesis today. Among other things, that algorithms solve problems means that, what do we mean by algorithms? Turing machines are a reasonable definition. Solving problems means deciding languages. It means halting, because if it goes off into this infinite loop, that Turing machine, even on one input, if it halts on every single input, infinitely many inputs except for one of them, that machine doesn't do anything. It doesn't decide anything. It can get stuck in an infinite loop, and we don't want that. So what I'll leave you with for the weekend to think about is, I really don't like that. In fact, if I'm in the world of C, Java, or Python, what I'd like is a static analyzer that would tell me whether or not I'm going to get caught in an infinite loop for any run of my program. Does such a static analyzer exist? There are practical static analyzers that can kind of do that, but the real answer is, the real question is, can you, given a Turing machine and an input X, can you determine whether or not that Turing machine halts and accepts or rejects? And the answer is a definitive no. We'll take a look at that on Monday.